Hi everyone, it's great to be here today. Have you ever wanted to program your GPU cluster as if it was a single GPU and not a cluster? PyTorch symmetric memory is bringing you one step closer to being able to do just that. It's a new paradigm in programming distributed AI. The story of PyTorch symmetric memory started in 2023. When we've noticed that a lot of our LLM inference workloads are bottlenecked by communication functions that are performed there, and my colleagues have already talked about it in their morning talk. So to alleviate those bottlenecks, we've wrote kernels that are using direct memory access to reduce the latency of those collective communications that we were performing. But we quickly realized that those direct memory access approaches would be useful for more than just those predefined kernels that are performing fast or reduced operations. So we generalized this concept, and in a few months, PyTorch symmetric memory was born. We landed a prototype implementation into PyTorch. We quickly went to work using it in multiple parallel schemes that we are using in PyTorch and tried to make it as convenient and ergonomic to use as possible. We didn't stop our work there, and currently we are working on going to multi-node scale, on implementing support for various hardware backends, and on implementing yet new fused and interesting parallelization strategies with symmetric memory. To recap, there are two main ways of organizing communication between processes. One is message passing, and it can be described as packing your stuff in a box, taking this box to a post office, mailing it. It adds a lot of latency to the process. It limits the stuff that you can send this way. It limits your flexibility as a developer to express the ideas that you want really well. Another way is when each of the processes that are participating in communication is opening up some shared memory region and allows other processes to directly access this shared memory region for reading and for writing. And this is what symmetric memory is doing. Taking this to the programming model level, we are allocating a portion of memory on each of our processors and are exchanging handles to this memory so that all the processors can directly access this memory and see the information that other processors want to share with them. It sounds pretty simple at the programming model level, at the conceptual level, but actually implementing it in a robust way, in such a way so that multiple developers using these systems can reliably use this access to peers' memory requires some uncommon knowledge, navigating through incompletely documented APIs, and finally, to be able to use this shared memory, you need to know when it's safe, for example, to write to it when there is nothing else happening, or when the other process has already prepared the data for you to read. And performing these synchronizations correctly also is pretty tricky and requires quite a lot of expertise. So with symmetric memory, we are providing pre-written synchronization primitives so that the developers don't need to think about that too much. So what capabilities that were previously unavailable does symmetric memory unlock? First, it's giving us very low latency kernels, so that the workloads that were previously latency bound can now run much faster. It also allows us to write kernels that are doing in-kernel communication and computation. And it allows us to implement truly arbitrary communication patterns that are currently not covered by existing communication libraries, such as Nickel or RICL. So for the rest of this talk, we are going to talk about how we are using symmetric memory in PyTorch currently, how you can use symmetric memory to write your own kernels, and finally, we'll talk about how we are scaling out to multi-node scenarios. So first, how do you use symmetric memory that's available in PyTorch today? We think we've come up with a pretty convenient way to do it. You just allocate some region of memory with APIs that are not much different from PyTorch currently is using for allocating memory and exchanging the handles between all the participating GPUs. After you've exchanged those handles, you can directly use pointers on the peer devices as if they were your local memory pointers. And after you've exchanged them, you can call the available functions that are using symmetric memory directly in PyTorch. Here I am showing an example of calling a one-shot all reduce. That's a very latency optimized implementation for all reduce for small message sizes. Under the covers, the kernel that's doing this low latency all reduce is shown on the right. It's getting all the pointers to the peer memory and is directly accessing the peer memory on the other GPUs after making sure that the data on them is ready using the synchronization primitive. Next example of using symmetric memory in PyTorch is tensor parallelism. My colleagues today already talked about tensor parallelism, but to recap, it's a way of sharding model parameters across multiple GPUs and sharing compute between those multiple GPUs. Depending on the dimension on which the parameters are sharded, you either have to do all gather to collect all your data before calling the matrix multiplication, or you have to perform reduce scatter in the end after performing your matrix multiplication. Those communication operations can become a bottleneck. And they are exposed. There is no compute to hide them with. So what can we do to alleviate this bottleneck? The solution is to split the matrix multiplication into even more parts and perform a single part of matrix multiplication while the necessary communication is happening in the background. To be clear, we could have implemented this even previously, even with existing nickel functions. But there are two problems with that. Today, nickel is using SM resources to perform sends and receives. And we already have a matrix multiplication going. So we want this matrix multiplication to use all the SMs available. We don't want to share those SMs for communication also. And second, we want to be able to use one-sided communication to be able to more easily write the parallelization schemes that we want. And with nickel, you have to call, send, and receive simultaneously on the both sides. Now, symmetric memory is helping us solve both of those problems. It's using copy engines to send the data between the GPUs so that SM resources are not busy. And it allows us to use one-sided sends. So one side can send the data to another, and another will synchronize and make sure that the data is received at some later point. So we have implementations of both reduce scatter and all-gather matrix multiplications in PyTorch, and they can be used both in eager mode and with torch compile. But as I've mentioned, this is something that we could have implemented before, even with symmetric memory. Now let's move on to next algorithm that was truly impossible to do before we implemented symmetric memory in PyTorch. And that is token shuffling that's frequently used in MOE models. Again, my colleagues already talked about how tokens are distributed during the MOE function in modern LLM models. But to recap, you have some sequence of tokens, and those tokens are sent to different experts that can potentially be on the different GPUs. And each GPU can get a different number of tokens. You don't know in advance how many tokens each GPU is going to get. These splits are first computed on the GPU, and on the CPU, you don't know the number of tokens that would go to any particular destination. Current communication libraries like nickel require all the metadata for communication to be available on the CPU. So if we were to use nickel for this, we would be required to do a GPU-CPU sync to send this data to be available on the CPU. We don't want to do this for performance reasons, because doing those things would make our computation much slower. So we use symmetric memory to write this all-to-all kernel that can read the metadata directly on the device. And this allows us, in turn, to use CUDA graphs to speed up our computation, and since our computation consists of many very small kernels, and now we are no longer limited by the launch latency for those small kernels, we are able to see 4x speed up just by using this all-to-all kernel that's using the data directly on the GPU. Now, let's move to the next part of my talk, where I'll show you how you can use symmetric memory to write your own communication kernels, so that you are no longer limited by whatever PyTorch, whatever Nickel, whatever Rickel offers you, and you can take your destiny in your own hands. To enable this, we are using OpenAI's Triton. Triton is a great Python DSL that has previously allowed a lot of people who are not expert GPU programmers to write very efficient GPU kernels. Now we wanted to turn it into a tool that allows people who are not expert network programmers to be able to write efficient communication kernels, and kernels that are overlapping communication and computation. And we are doing this with symmetric memory. Here is an example of a Triton kernel that's using our symmetric memory pointers. As you can see, it looks just like a regular Triton kernel. You are sending some tensor arguments as arguments. You are sending the rank of your process so that we are able to see where we are at. And everything else looks pretty much like normal Triton kernel you would write for anything else. You read some data, you perform some computation on it, you write it back. The only noticeable difference here is first you have to synchronize to make sure that everyone is ready for communication. And we are providing a primitive for that with very readable parameters so that you exactly know what parameters to call it with. And after that, you're on your way. You can read your data, you can perform any compute that you would do in Triton on this data. You could do any fused normalizations, any fused quantizations, anything you want in this kernel, and you can freely access your peer's memory and write the resultant data if you want to write your data to the peers. So previously, we have been focusing on the intranode communication, things that you can do while your workload can fit on a single node. But now the world is getting bigger. We want to scale our models to the multi-node scenario. Even inference now requires multiple nodes, as you've probably heard today. So how can symmetric memory help us in the multi-node scenario? In the multi-node, we can no longer directly write to the peer's memory, and NICs, network interface controllers, come into play. Traditionally, even when NICs can directly access GPU data, the metadata preparation and ringing the doorbell is done on the CPU. And even if the communication is initiated in kernel, there is a CPU proxy thread that's monitoring the kernel for communication requests, preparing the metadata, and ringing the NIC doorbell if the message needs to be sent. This is working. This is a good approach. It has been working for multiple years, but what we want to do is let GPUs, not CPUs, talk. Why? Because modern NICs can actually process the messages at a massive rate, hundreds of millions of requests per second. When we have just a single CPU thread, it cannot saturate this rate of messages. And if we want to do a fine-grained communication when we are sending small messages because we want to implement some custom algorithm that doesn't require us to send megabytes and gigabytes of data, we want to saturate the NIC with small messages, and for this, we need to be able to originate messages directly on the GPU. What advantages does this give us? Shorter initialization time, massive message rate that can saturate modern NICs, and we are still getting the remote direct memory access that we were previously getting with the IBRC approaches. How is symmetric memory in PyTorch using this? We adopted NVSHMEM as one of our backends. And for internode communication, we can use NVSHMEM as symmetric memory backend. And similarly to previous example, we are allowing people to write Triton kernels that are directly calling NVishmem functions to manipulate the data and send them between the GPUs. This example shows how you can send the data from one GPU to another using NVishmem primitives. One GPU is sending, another GPU is receiving, so each of them is calling their corresponding NVishmem functions. And the only thing you need to do on the host to enable this is to call enable Triton so that NVishmem plugin is loaded to the Triton kernels. Again, this is a pretty ergonomic scenario. There is a subtle difference from the previous Triton kernel that I have showed, in that previously we were getting as many pointers as there were ranks in our communication. Here for NVishmem, we are getting just one handle and explicitly sending the peer argument, the peer that we want to talk to, as an argument to an NVishmem call. Please excuse our inconsistency here. We are still trying to come up with the most ergonomic and convenient APIs, and with your help, I'm pretty sure we'll get there. So, are we done here? No, not at all. We still have a lot of plans and a lot of new capabilities that we want to enable with the symmetric memory. We want to support heterogeneous hardware. Currently, we are supporting AMD ROCm as a backend for the intranode, but ROCm also provides a ROCshmem library that's very similar to NVishmem, and we want to add support for ROCshmem also. We want to support new data types, new quantized types that are used on the modern GPUs. We want to support new novel algorithms. We have all-to-all dynamic implementation, but things can always be made better, so that we are doing things more efficiently and in a more fine-grained manner. Finally, we want to leverage Torch compile so that it's not just developers who are able to write those communication and computation kernels, but they could be auto-generated for you in an automatic way. Finally, in all the things that we've discussed now, we've assumed that everything always goes fine and no GPUs ever go out of order, no GPUs hang, nothing happens. That's far from true, as many of you know. Something always happens, errors are thrown, and being able to gracefully handle those error scenarios, being able to diagnose what exactly went wrong, what node we have to replace, what we have to do, is something that we also want to add support for in symmetric memory as a first class. So what are the takeaways that we have from this call? I hope I and my colleagues previously have convinced you that remote access, direct memory access is something that's really important for modern LLM workloads. And also another thing that I want to bring down is that we cannot predict what exact algorithms you want to implement. We cannot predict what exact computations you want to do. So PyTorch distributed is turning into a developer tool from the package that we used to be previously, when we were just providing pre-written routines for what we thought you would need. This is no longer enough. We want to engage with developers and to give the developers tools to implement the exact computations and overlaps and communications that they need. So we are a community here. Please join us in contributing your favorite kernels to PyTorch and in using PyTorch symmetric memory to solve your problems. And as this is a networking at scale conference, right? So we all know here that the network is going to be important, that the scale of all the things that we are doing is growing, and we should support the ever-growing communication requirements of our workloads. And symmetric memory is one of the ways to do that. Thank you.